standard deviation of this martingale turns out to be the size of the boundary at the current time. And you can easily intuitively see the more boundary you have, the more chance you have to move the set. So in the places where your updates are costly, you move quickly out of those areas. And in the places you care about where the conductance is small, but you still have to run to see can I improve it even further, in those places each update is very cheap if you keep the right data structure. So I'm going to, so this is a picture shows what is the data that the algorithm is actually keeping. It's only keeping the data along the boundary and only needs to update that. Okay, I'm going to finally show you just some examples. So this is a plot of the volume versus time in one sample run. And you see that here the process, it looks like it's almost dying here, of course, conditioned not to die. So here it reached like 1 or 2 points, but then it, it moves up, and here it finally gets absorbed in the whole space. This is some graph showing just one example of performance versus the truncated random walk algorithm, and the blue points represent what you get from the random walk. So here is the volume of the set we found, and on the y-axis we have the size of the cut. So what we want is to get really the smallest, the smallest height here, the smallest cut size for a given volume, and the red points represent experiments of the evolving set process, and one sees that it always does at least as well in this sample as the random walk based process, but there's room for a lot more experiments in many more settings. And so there are many open problems here on how much the logarithmic terms can be reduced, and finding local algorithms for other problems. So it's kind of a perspective, again, was introduced by Spielman and Teng, of you have a huge network, look at any kind of graph algorithm that you are running on it. Can you run this algorithm locally around specific nodes of interest without having to look at the whole infinite graph, or at the whole huge graph? I don't know if there are any questions, otherwise I want to move to the second part of the talk. Maybe you'll take questions later. So the second part is kind of a seemingly related problem, but really in a different setting. So this is setting of interest in theoretical computer science, but recently, largely due to the work of Philippe Rigolet, there has been strong connection of that to problems in statistics. I'll mention a bit of that later. So what is the problem here? So this would be a graph very different from the example of the web. So this is a graph, we start with a graph which is Gn1/2. So we have n nodes, and every possible edge is present with probability half independently of every other edge. And we're looking for a clique in that graph. So a clique is a complete subgraph, something where all the edges are present. And we want to find the maximum clique, or a large clique. So it's kind of philosophically related to the previous story where we were trying to find a relatively dense set. Here we're trying to find a maximally dense set, but it's quite different setting. There the main interest is in graphs that arise in practice that tend to be huge but have bounded or logarithmic degrees. Here we're looking at graphs which, well, can still be huge, but every vertex is connected to half of the other vertex. Okay, so just to notice the settings are different. Now finding the maximum clique is a NP hard problem. So and it's known even hard to approximate. But these NP completeness results apply to worst case graphs. So what about average case, when we really pick the graph at random, like I said, as g n half? So in g n half, again, every edge is chosen independently. So it's now, how large is the largest clique? So this is very easy to compute using first and second moments. So if you have a set of k vertices, you can calculate what's the chance that this set is a clique. We have a k choose 2 edges. So we just have 2 to the minus k choose 2, the chance this set is a clique. So I can count the expected number of cliques, n choose k times this 2 to the minus k choose 2. And then I, certainly in order to see a clique of size k, this expectation had better be substantial, bigger than 1, otherwise I'm not going to see such a clique. Now, even if the expectation is bigger than 1, that doesn't tell me that I'll see such cliques, because maybe the expectation is coming from a small probability event of many. So, but that's where the second moment method comes in. We can compute the variance of the number of cliques, and see that in this case, really once k is below 2 log n, and the log here is actually to base 2. So once k once k is less than 2 log n, then the first moment is large and the variance is small enough, so we really will get cliques of any size less than 2 log n by a very simple kind of counting and computing first and second moment argument. However, this argument doesn't allow us to find such a clique. How about finding it in polynomial time in n? So the most naive greedy algorithm will find you a clique of size log n. Again, log to base 2. You just pick any node you like. That's v1. Half the vertices are its neighbors, right? So choose v2 to be one of these neighbors. Now v1, v2, how many vertices are common neighbors of v1 and v2? Well, very close to n over 4, right? So we pick one of those to be v3. And we just iterate. After we picked k vertices, we have n over 2 to the k vertices are still common neighbors of these, and there's very good concentration. So we can really keep going for log base 2n steps almost. And so the most naive greedy algorithm will construct clique of size log base 2 of n. And in fact, since we have a lot of freedom as we go along this construction, we can find many cliques of size log base 2n very cheaply. But the best efforts of science have not yielded a clique of size 1% better than that. So we know out there are cliques of twice log base 2 of n, but no one knows how to find even 1% better than log base 2 of n. So this is one challenge. Very, very hard, but maybe, the right idea has been missing. So people thought, well, since this problem is hard, how about let's try and make this easier for us by planting artificially a large clique. So this will be the graph model g n half k. We start with g n half, randomly choose k vertices, and add the edges between them, the missing edges, to form a k clique. How large should this k be so that we will detect this clique? Okay, and the k of interest now will be a power of n. So if we take k to be, say, n to the quarter, so we're planting artificially a clique of size n to the quarter in a place where the normal size cliques are at most 2 log n. The question is, can we even detect that this happened? That is, if I give you two samples, one is the original g n half, and one has a planted clique of size n to the quarter, can you detect this? Well, how much time? And how can you detect this in polynomial time? Because if you have, time n to the log n, it's very easy. You just go over all subsets of size 3 log n, and if there's a clique of size 3 log n, then you know this is part of the planted clique because it doesn't occur in nature. It is in g n half. Okay, but that's n to the log n. It's not polynomial time. Okay, so now if k is bigger than root n log n, then life is very easy. You can just take the vertices of highest degree, and these form the clique, because the degree of every vertex is binomial n1/2, so approximately Gaussian with a mean of n over 2 and variance of also order n. So we'll see fluctuations of root n typically, but the largest fluctuation we'll see is order root n log n in the original graph. So if we plant a clique of size bigger than constant root n log n, then just the degrees will tell us these are the vertices of the clique, and it's very fast to compute degrees. Now, the best efforts of science have only improved this by removing the root log. Okay? So we still don't know anything about n to the quarter or n to the 0.49. So, but for root n, there are various algorithms that succeed in locating this clique in polynomial time. For little o of root n, there's no known algorithm in polynomial time, and that's still the case. The first algorithm was a spectral one due to Noga Alon, Michael Krivulevich, and Benny Sudakov. You look in the second eigen, so it's fast to approximate the eigenvalues of the adjacency matrix and the eigenvectors. You look at the second eigenvector, and you look at where the largest components of that eigenvector are, and if it's larger than constant root n, this will work. This is still not a linear time algorithm. So what computer scientists mean by linear time here is actually n squared, because the size of your data is n squared. To record a graph on n nodes, you need an n by n matrix. So this algorithm is pretty fast, but it's not linear time. It takes more than n squared to find this eigenvector. So Feige and Ron in 2010 suggested a different method which works just as well in practice as the spectral algorithm, but they couldn't analyze it all the way. And the method, it's interesting philosophically, instead of looking for the winners, you just weed out the losers. So you look at the vertices with lowest degree, look at the vertex with lowest degree, remove it, and keep going. And the vertices you left with in the end should be the clique. And experimentally, this works well when the clique has size root n, but they could only prove it works with some constant probability. Now note that their algorithm is not randomized. Their algorithm is completely deterministic. So what constant probability means is, half the cases they will fail, or at least they cannot guarantee success. However, inspired by the algorithm, we came up with a variant which is guaranteed to work, and that is with probability fast approaching 1, it will work for cliques of size constant root n. And in retrospect, it's very natural algorithm for anyone doing something like machine learning. It's a ridiculously simple algorithm. You'll see it in a moment, but we don't have essentially anything better than this. So let's start with a clique of size 2 root n. And what we want to find is the k vertices of the hidden clique. And the error probability will go pretty quickly to 0. This is the probability this will fail. Okay, so the first phase. So these purple nodes are the nodes of the clique, but the algorithm doesn't see them. They're just here for illustration, but the algorithm doesn't see them. Now, what we do, we pick a random subset of the vertices which contains every vertex with probability a quarter. This is these nodes, the red nodes, and for the remaining 3 quarters we record what are the degrees, but just the degrees in the red part. Okay, so this is these numbers. So this vertex here has 2 neighbors in the red part. This vertex here has 4 neighbors in the red part, and so on. Now the red part is random, so of course it will contain some vertices from the hidden clique and some mostly outside. Okay, so that's the first phase. Now, in the next phase, we're going to, first of all, throw away all the red nodes, and among the rest, keep those that had more than the median number of neighbors in the red part. So we do thresholding in the non-red part according to the number of neighbors in the red part, and we keep the better half. So remember, the red part was 1/4, so the rest was 3/4, and from those we keep the best half. So we're left with 3/8 of the original graph. So that's why n prime here is 3/8 n. Now what about the clique vertices? So what happens with the clique vertices is that for vertices in the clique, it's actually easier to pass the threshold in the first round because they have neighbors in the red set that happen to be in the clique. And the threshold we used n/8, which is the mean for normal vertices. For vertices in the clique, this threshold is actually below the mean because they have a boost coming from their friends from the other clique vertices that happen to be red. And this boost helps them. So the number of clique vertices that survive in the first round, a very simple calculation, tells you that it's a little better than 2 root n prime, just by 3%. This is a very standard calculation you can give to your undergrad. But now we're in the same type of problem with n prime replacing n, k prime replacing k, but things have improved a little bit by 3%. The key is that we have not looked at any of the edges connecting the n prime vertices we have focused on. We only compared degrees into the red part. So we really have a new instance of the same problem. We have a random graph g n prime half with a planted clique of size k prime that's a little bit bigger. So we can iterate the procedure again, and we'll gain at least 3%. Actually, it's a phenomenon of the rich get richer. So if we start at 2.06, we'll get a little more than 3% even. But anyway, once we iterate this, say log n times, the proportion of the clique inside the graph we have will improve enough that then we can just finish off by just using degrees, because we'll get above this root n log n threshold I told you about in the beginning. So we just have to iterate this a very small number of times. And also each iteration is cheaper because the graph is going down geometrically. So really the first step takes most of the complexity. So that's really the whole algorithm, just this one very simple calculation with with a binomial approximation, Gaussian approximation to the binomial does all the work for you. Yes?
How it's different, all those heuristic by generating random correlation structures?
Random
correlation structure, heuristic.
Okay. So this is again, this is not heuristic. This is a rigorous algorithm that is guaranteed to work for this problem. But as I mentioned in the beginning, it's very natural and very closely related to a lot of methods, standardly used on other problems. I have two things to say just to finish. One is this. I told you this works for 2 root n. What do you do with a smaller constant? So suppose you have the clique is size root n over 10. This method will fail, but as will the other methods, the spectral and all the methods fail if you just apply them as it is. And for root n over 10, we don't know any method which is linear time. But what one can do, as suggested in this original paper, pick a random vertex v and just look at the neighbors of v. Okay? This reduces the graph from n to n over 2. And if you happen to be lucky and the v you chose was in the clique, then you're going to retain the whole clique. So you improve the constant by a factor of root 2. Because k has remained the same, but n was cut by 2. So then so this will work as long as the constant, as long as the clique is at least root 2 times n, and you can repeat this several times. But each time costs you a factor of root n in the complexity. So in polynomial time, you could do any constant root n clique, but if the constant is very small, then the degree of the polynomial is very high. And then there's nothing better than this that we know even now. So I don't have time, but I again want to emphasize that there are connections of this to computational problems in statistics, first pointed out by Philippe Rigolet, and there's a relevant paper of Nobel and Son and many others in statistics, where if you look at Gaussian matrices and look at sub-pieces with large correlations, finding those pieces can be reduced to the hidden clique problem. So far, this reduction is mostly to prove negative results. It's to prove that certain problems that have been known experimentally to be computationally hard in statistics, well, there's a good reason. They're not just hard for us, but they're hard for this whole large community that's been looking at the planted clique problem for 20 years. So, but on the positive side, if you have any idea for these problems, probably the difficulty is the same for all of them. There are various papers now that show that you cannot do better than root n if you're in a restricted class of algorithms, things that are just spectral or just basically looking at degrees as we've been doing here. But there's nothing that says that a really new idea might find anything of size n to the epsilon. So it's really one of these cases, unlike NP hard problems, where we really don't know where the truth lies. Is this polynomial or not? Thank you for your attention. Yes.
So in all this, in the second part, you started with Gn half.
Yes.
Is that half very critical?
No, everything works.
So it is still 2 log n regardless of the word G and P.
No, the constant.
Oh, the base of log is P.
Yeah, the constant is affected, but everything is the same. Also, instead of hidden clique, you could ask, I have a graph G and P, and I want to locate a denser subgraph which looks like G and Q, and it's all the same. Just changing the constants. I want to emphasize that the talk tomorrow is totally independent of this one, so if you've suffered today, you have a completely fresh chance to suffer tomorrow. Independent chance. Yes?
I have a question about your first talk.
Yes.
Is it possible to obtain a global partition, maybe sampling the whole graph according to the degree, and then running your algorithm in parallel?
It is, in fact, it seems best to do it sequentially by biting off pieces, but if you want to do it parallelly, you could. But the thing is, in that case, it doesn't seem to be the state-of-the-art algorithm. That is, it doesn't do work as fast as some, say, spectral-based algorithm. Yes.
I have a question about the end game. Yeah, I think you skipped over the slide. I mean, in the end of the process you were describing, where you were choosing.
Oh, yeah.
In the end, of course, you have a subset of the clique that you're looking for.
That's right.
So
Sorry.
Then it's relatively simple to identify the elements of the clique once you have that small subset.
That's right. So this problem, the hidden problem, once you have your foot in the door, it's very easy to pry it open. That is, once you have, a number of vertices from this hidden clique, if you just look at their common neighbors, that's going to tell you about where is the so the size we find. So we still have a lot of vertices when we stop the algorithm. So it's a small portion of the planted clique, but it's not a constant number of vertices. It's a large number of vertices. So, and we know that everything in the original clique are common neighbors of these. So just that will allow us
to
to...
the complexity of finding that, the stuff that's
Yeah,
left out, isn't it?
the complexity of finding what's left out is very small.
Other questions? If not, let's thank Professor Perez.